Hello. Today we're going to be working on finding complex roots. Last class we did factoring to find complex roots, and we're going to deal today with what happens when we can't do that. So we're going to start with an example from last time so that I know a lot of people struggled with this section, with the 7-2 section. So first off, the question here is, will this graph have, and when it says sketch it, that's for the warm-up, so you can ignore that part. Will this graph have imaginary roots? And so one thing we know about this is we have one real root at -4, 0, and this has that little point of inflection that cubics have. We also know from the equation that this is a third-degree polynomial, which means it's going to have 3 roots. Now, because it only has one real root, we know it's going to have 2 complex roots as well, so 2 imaginary roots as well. So we want to find the factored form. I'm going to move that a little bit. So I'm going to make my 2x3 table here, or area model. So I know I have I know I have a real root at -4, 0, so my factor is going to be x plus 4. I'm going to put my first term there, x to the third, pull out that x to the second, 4x squared. So I have a 4x squared already. I don't need any more, so I'm going to add 0x squared here. Factor out 0x. I don't really need the x and the x squared with those zeros, but to keep it consistent with the pattern, it helps a little bit. 0x times 4 is going to give me 0x. I need my x term to be 9x, so I'm going to add 9x, factor out a 9, and then multiply 9 times 4 to get 36. So my factored form here, my partially factored form, is y equals x plus 4 times x squared plus 9. Now, if we're factoring x squared plus 9, it looks a little bit like a difference of squares, except for it's not a difference, it's a sum. And so that really doesn't help us with the, difference of squares would have been x plus 3, x minus 3 times x minus 3. But this is going to work similarly, except for we have to deal with the imaginary part of it. So the way I'm going to get to that point is by using the zero product property to find my roots. So we already know here that this is going to be x equals -4. And if I take this x squared plus 9 and set it equal to 0, I'm going to solve for that one. So subtract 9 from both sides. I've got x squared equals -9. Actually, I'm going to leave myself a little bit more space there. And then to solve this, I'm going to square root both sides. And one thing we need to remember when we square root to solve is that we have both a positive and a negative answer there. So I've got x equals plus or minus the square root of -9. Now off to this little part up here. I'm just going to get it out of the way. From 7-1, we dealt with the square root of negative numbers. So we're going to split that into the square root of 9 times the square root of -1. Square root of 9 is 3, and the square root of -1, as we found out in 7-1, is the letter I, the imaginary number I. So this is going to be x equals plus or minus 3i. So I have, for this equation, I have a real root at -4, an imaginary root at 3i, and an imaginary root at -3i. So my factored form, because whenever we write our factors, it's always the x minus the root. So x minus a -4 is going to give me x plus 4. X minus 3i. And x minus a -3i, which is going to give me x plus 3i. So what you can see here is that this part right here, this x minus 3i, x plus 3i, looks very similar to the x minus 3 and x plus 3 that we learned with difference of squares. But now it's a sum of squares. It's going to work in a very, very similar way. So if you can see that pattern, you don't need to do all this. But if this makes more sense to you, then you can do all that. So today what we're going to be doing, this one worked out nicely so that this was factorable or solvable in another way. What we're going to be doing today are problems where what we get here, or a quadratic that we have here, can't be factored. So today we're dealing with the quadratics that have complex roots and we can't factor them. So what we're going to do instead, our other method of of solving quadratics, is the quadratic formula. And we know this one, if we look at this parabola, we know this is not going to have any real roots. It's second degree, but it has no real roots. It doesn't cross the x-axis. So this is our equation, x squared minus 4x plus 5. And so I'm going to take this up a little bit, straighten that out. A couple things to note about the quadratic formula. In the formula, it's negative b. A lot of people tend to forget that negative exists in the formula, so watch your negatives. Here we square b. Remember that a negative squared is always a positive, so be careful when you put that in the calculator, and we'll talk about that more. So if we look at our equation here, 0 equals x squared minus 4x plus 5. The number in front of the x squared is our a value. In that case, this is 1. The number in front of the x is negative 4. That's our b value. So negative 4. And our c value is 5. Yellow's not showing up terribly well, but we'll go with it for now. So we're going to put all those in. Just be aware this little nice setup we have here is going to exist in a couple of places on the worksheet, but it does not happen automatically. You do need to have that quadratic formula down and know where to plug things in. So x equals negative b, so I'm going to put in my negative 4 here, plus or minus the square root of b squared, so negative 4 squared, minus 4a, so 1, and then c and 5, and then all divided by 2a, so 2 times 1. So what we want to do is take, I'm going to do it and then I'll get rid of it. We're going to take this part right here, and we're going to calculate that without the square root. We've often done that just in the calculator with the square root sign, but if we do that this time, what'll happen is we'll get an error, and that's not going to be very helpful to us. So we're going to take that negative 4 squared minus 4 times 1 times 5. Now, if you just put that in the calculator exactly like that with the parentheses, you're going to get what you need to get out of that number. But I also want you to use your brain, so I'm going to show you how to just do this step by step. So negative 4 squared is a positive 16, minus 4 times 1 times 5. So I can do this, look at this a couple of ways. I can look at this as minus and then just multiply 4 times 1 times 5, which is going to give me 20. Or I can do negative 4 times 1 times 5, which is going to give me negative 20. I just need to be careful how I consider that negative or that minus and not do it twice. So 16 minus 20 gives me negative 4. Now, in the past, when we've ended up with that situation, we've said no solution. We're not going to do that now because we're into imaginary numbers. So I'm going to simplify all this. Negative 4 is positive 4, plus or minus the square root. We just found that as negative 4, all divided by 2 times 1, which is 2. So again, what we used to do is say this has no solution. Now what we're going to do is put this in terms of imaginary or complex roots. So when we look at this and we take that square root of negative 4, this part you don't have to show. You can just do this, but I do want to show it for people who are still struggling with this. Square root of negative 4 can be split into square root of 4, square root of negative 1. Square root of 4 is 2. Square root of negative 1 we write as I. So this is going to be x equals 4 plus or minus 2i divided by 2. So at this place, when we had real numbers, we just split it into the positive and negative. We're not going to do that here because that's not going to help us, because when we look at 4 plus or minus 2i, we're not going to be able to combine anything with 2i unless it has an I. So we're just going to simplify this if we can. In some cases, you're going to get to this place, and it's going to be as far as you can go. However, in this case, 4 and 2 are both divisible by 2. So I can kind of look at this as, let's see, as a side note here, as 4 over 2 plus or minus 2i over 2, because that's the same thing if I have the denominators the same. So that one's going to give me x equals 2 plus or minus I. So those are my roots. I have roots at 2 plus I and 2 minus I. Those are my two roots. Writing it in factored form, remember for the factors we do x minus the root. So I'm going to do x minus and then put in 2 plus I. That's going to be one factor. I'm going to put brackets around that for now. And then my other one is going to be x minus 2 minus I. I'm going to put brackets around that as well. I can simplify that further by distributing just the negative. So I'm going to do x minus 2 minus I and x minus 2 plus I. So this is my factored form, and these are my roots, my imaginary roots. And one of the things we can also do, I'm just going to do this one time, is check and make sure that that factored form is actually correct by multiplying it all out. So I'm going to take a 3 by 3 box. I'm going to do x minus 2 minus I and x minus 2 plus I. And then I'm going to multiply each of these areas, find each of those, and combine my like terms. So x times x is x squared, x times negative 2 is negative 2x, x times negative I is negative ix. Down at the bottom again, x times negative 2 is negative 2x. Negative 2 times negative 2 is a positive 4. Negative 2 times negative I is a positive 2i. X times I, ix, or xi, it doesn't really matter which. Negative 2i and negative I squared. And there's a couple things that we can get rid of right off the bat. 2i and negative 2i are going to add out to 0. ix and negative ix are also going to add out to 0. So then it's a matter of simplifying what I can. So let's take this negative I squared and replace I squared with negative 1. So I've got double negative 1, so that's going to be plus 1. So my standard form here, I'm going to take my x squared for my first term. Negative 2x plus negative 2x is negative 4x. And then 4 plus 1 is going to give me plus 5. And that is the equation that I started with way, way back. I'm shrinking way out here in the beginning. So that can tell us, that's a way to check, because it's hard to check with complex roots. You can't really check them on the graph to make sure you got it right. But that's how you can check that you have the right factored form. All right, so we'll do a couple of examples. We'll just run through this pretty quickly. We have a of 1, b of 10, c of 26. So the quadratic formula, again, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Get that written down somewhere if you don't have it memorized. So negative 10 plus or minus 10 squared minus 4 times 1 times 26, all divided by 2 times 1. So I've got x equals negative 10 plus or minus the square root of, and this would give me 100 minus 104, so negative 4, all divided by 2 times 1, which is 2. Square root of negative 4, I'm going to write that as square root of 4 times the square root of negative 1, so 2i. So I've got x equals negative 10 plus or minus 2i, all divided by 2. 10 and 2i are both divisible by 2, so I'm going to write that as x equals negative 5 plus or minus I. So those are my roots. And my roots can give me my factored form as long as this is just an x squared. Keep in mind, it's really important to remember that the quadratic formula finds your roots. You have to do a little bit more work to find the factored form. So the factored form is going to be x minus, so x minus negative 5 plus I, that's one of my factors, and x minus negative 5, minus I. That's my other factor. To simplify that, distributing that negative, not that x, so I've got x, and then this is a negative, negative 5, so plus 5, and then minus I times x plus 5 plus I. So that's my factored form, pardon me, of this equation, of that beginning equation. All right, the last one, this one is going to be a little different because we don't have an a value of 1, so I wanted to make sure to look at that. So a is 3, b is 7, c is negative 6. So negative 7 plus or minus square root of 7 squared times 4 times 3 times negative 6, all divided by 2a, which is 2 times 3. So I'm going to simplify here. So I've got x equals negative 7 plus or minus. If I take this whole part right here, whoops, that gives me 49 minus 4 times 3 times 6, which is 72, negative 72. So minus a negative 72 or plus 72. So 49 plus 72, 121. So this is the square root of 121, all divided by 6. Now, I don't have a negative under the square root sign here. I actually have a positive that is a perfect square. So this one is going to have real roots, and that's not always going to happen. But I also wanted to show you what happens with the a value. So this equals negative 7 plus or minus. The square root of 121 is 11, and then all divided by 6. So I'm going to split that into my positive and negative, which I can do this time because it's not an imaginary number. So negative 7 plus 11 divided by 6 is 4 over 6, which is 2/3. Negative 7 minus 11 over 6 is going to give me negative 18 over 6, which is going to give me negative 3. So I have real roots at 2/3 and negative 3. So I can write my factored form as x minus 2/3 times x minus negative 3, or x plus 3. The problem with this, and this is the problem with the quadratic formula in factored form, is it gives you just the roots. If I multiply this out, I only have x squared for my first term. But my first term, if I scooch this out, is 3x squared. So what happens if I just put a 3 out here? Let's check and see if that works. So if I say this is my factored form, to multiply that out, I'm going to just multiply this into the first part, so 3x minus 2 and x plus 3. I can use the box for this. I can also just use distribution. So 3x squared, 3x times 3 is plus 9x, minus 2x, minus 6. So 3x squared plus 7x minus 6, and that is, in fact, what I started with. So right here, erase that little part. Whoops. Whoops. Just screwing up all over the place. Right there is my factored form, and those are my roots. So that'll work as well with the imaginary roots if you have an a value that's not 1, but I wanted to show that to you as well. So that is 7-3. Hopefully that helps you out, and have a good day.